So welcome all. Today we are learning something about syntax directed translation as well as semantic analysis. So basically till now we have seen our parsing phase, and what we know in parsing, we get the result of parsing. Result of parsing was a syntax tree or a parse tree, right? So you get a tree. Now the thing is, parsing just says that yes you have the syntax is correct, right? But now just the syntax is correct is not enough for the proper compilation of your program. What you need is this some more things, like ultimately you have to generate code for it, right? Maybe you can call it intermediate code. So but you have to generate code for it. So just syntax is correct is not enough, right? So once a syntax is correct, we have to understand the meaning, right? So in syntax directed translation, what we will do, along with the grammar, we will have some semantic rules also. Okay, in SDT, let me write syntax directed translation as SDT. So in SDT you will have your grammar. Along with the grammar, we will have semantic rules. Okay. So now what will happen once, according to the productions of the grammar, once a production will reduce, then these semantic rules will be applied, and the corresponding things, whatever we want to do, we can mention here. Like we can want to execute some set of codes, it can be written here, right? Now suppose you will have some tree, right? So trees will be like something, some nodes and some derivation, some these kind of trees, right? So all these will be certain nodes. There was a particular expression which has to be calculated, and now it has been represented in this tree. So suppose this was E, which gives E plus E, and E gives something this plus this, right? So what is happening, if you start from bottom, you will have certain values here, certain values here, and these values, suppose it was multiplication. So here on this node you will have to store the results of these multiplication, right? One production has to be reduced here, right? One production was E gives, suppose it was something ID into ID, so this production is reducing here. So if this production is reducing, now whatever values calculated here has to be stored for this node, right? So for this purpose, what will happen, each node here in this tree will have attributes, okay, some properties. So some attributes they will have, in which certain values can be stored, and in last you can have the final values here, no problem. So this is what we are going to see here in this video. What we are going to see, let me show you one thing. Suppose you have a program, right? And in this program you want to say that This is the code, and in this code you want to compile this code. So what are the things you are going to see, right? Whether all the syntax is correct, it is written nicely, written correctly or not, it supports our grammar or not, right? Now what else you want to see for the grammar? Tell me. You will see something about whether the variables have been declared correctly or not, whether the variable which we are using has been corrected or not. We are doing some assignment operation, whether they are y is assignable or not. So these all certain different kind of things we are going to see, right? Does a method call have the right number of types and parameters or not? So could p be null when p.q is executed? So these are certain things which can be considered as a semantic, right? What else do we need to know? Suppose where the fields are allocated in an object, right? How big are the objects, how much storage will be needed, and these kind of information, right? So what you are going to do, here basically, as we have seen, what we are going to say is suppose in semantic analysis the main task will be to extract type and other information from the grammar, check language rules that go beyond the context-free grammar. Okay. Now the key data structure is symbol table. You understand about the symbol table. As we have seen, a symbol table will be a data structure where you will store the information related to each identifier. The identifier along with its other information like kind, type and other related information. Storage location for variables, other annotations. Okay, so these kind of things you will have. So information can be like suppose in symbol tables generated from declaration, right? When you will declare, from there this symbol table entries will be generated. It will be used for to process this expression and a statement. Similarly, type information is there, constant or variable information is there, register, memory values and other constant values are there. So these all will be generated in the program and will be used while processing, right? So for each language construct, we want to know what semantic rules should be checked. For an expression, what is its type? For declaration in a particular, what information needs to be captured? Suppose this for id has been declared and is in a scope. Constant, inferred type and value are explicit. Binary operators, the operator which will operate on two operands. Some expression 1 op, expression 2. So expression 1 and expression 2 have compatible types or not, right? Identical or well defined conversion to appropriate types. Inferred type is a function of the operator and operand. Now here expression is assignable. Expression 1 or 2 have compatible types. Okay, so inferred type is type of expression. Location where value is stored is assigned by the compiler. So whether the type casting is being done or not. field reference exp.f you are using, so exp is a reference type or not. Method call you are making exp.m, so exp is a reference type. The class of exp has a method named m, and these are certain things that we have to check. So basically what we are checking here is so many things. One more thing can be return a statement. Let me see, a return exp. So the expression can be assigned to a variable with a declared type of method, right? So these all sort of things can be done. So in semantic analysis, partial build abstract syntax tree we have. Now we need to extract semantic information and check constraints. So we can sometimes what we can do is during past time we can organize separate phrases, and some things can't be done on the fly. We can do it later on. What we can do, the semantic rules can be applied later on. Now we understand all the informations are stored in symbol table, and it can be generated by semantic analysis used there and later also. Now for these things, as I told, we will get a abstract syntax tree, and now we need in this tree that all nodes will have certain attributes, right? So let us think about attribute grammars. Attribute grammar means now we want to give some semantic things or some attributes to each productions, right? Okay, some semantic rules as well, right? So attribute grammar sometimes used directly, but even if ad hoc techniques are used, attribute grammars are useful. So what you can do is you can associate attributes with each node in the abstract syntax tree. Okay. So what can be the attributes, like type information, storage location, whether they are assignable or not, what is the value, current value, and different whatever attributes you want to store for your purpose of use, you can use them. You can use it as x.a if a is an attribute of node x. Okay. So attribute example can be val. You can use certain attribute dot val. You can use it. Okay. Now these attributes can be of two types. Basically, let me write it here. These attributes can be of two types. They can be synthesized or they can be inherited. Okay. So what happens, suppose there is a node A and it has child nodes, suppose x, y, z. In that case, what will happen, if A has some attribute a dot s, so it can have these values from its children, so it can be a function of, suppose x dot s, it can take values from x dot s, or it can take values from y dot s or z dot s. Okay. Now in inherited, what can be done? In inherited, actually the same thing. Suppose a is there, x, y, z are there. In that case, you can have the values from x dot I, y dot I, and z dot I. Suppose a was something like a dot I you were having. So here you can have synthesized attributes along with inherited attributes. Wait a minute. What are inherited attribute means? We are getting the value from the parent. Okay. So here z dot I will be function of either a dot I or their siblings, x dot I or y dot I. Okay, so we are talking only about attributes. Later on we will see some other things also, but attributes can be of these two types, where it can be synthesized as well as inherited. In synthesized, what will happen? We will get the values from the children, right? In inherited, what will happen? We will get the value from either the parent or the siblings. Okay. So this is how this works. So now if I tell you about an example, let me tell you about the same example. Okay, let me take example from the slide. So suppose this is the grammar. Program is declaration statement, and this declaration will be int id, expression is equal to expression this thing. Okay, we understand, we have seen this grammar earlier also. Now if I tell you about the attributes, so we can have certain attributes like env for environment. If you want to keep some information, type, kind means variable or value, what is its kind. Type can be integer kind of these that types, right? So these type of information, if you want to store, we will consider it as attributes. Let me show it in your next example. Suppose this is the grammar, and these can be certain attributes. It can be environment, type, and kind. So for declaration, if we are using, suppose declaration is int id, so what you are associating one rule, which is declaration.env is some certain values you are assigning it. It is identifier, it is int, and variable. Okay, so keeping these information, if you want to keep this information in EAV, it has been done. Now it is not the only thing that only one this thing attribute can be assigned. You may have multiple attributes as well. If we are talking about env only, this was the case of declaration. Now if we think about program here, it is what it says, declaration statement. Now a statement.env is declaration.env. We want to do like this. So environment can be copied. Okay, I am copying. We can have different other things as well. Suppose we are having expression is equal to 1. So what happens? Expression.kind is equal to val and type is equal to int. This is what we are going to store. If it was id, what will happen? Expression is id. Then in that case you will have type is equal to expression.env.lookup id. Okay, we are having a function. We will call this function and then find out what can be the environment of this. Okay, so what here we are saying is we can write different code, we can call a function, we can whatever we want to do, we can do here. Applying when this production will reduce, these are certain things which will be executed, right? Now for addition, suppose this is in, so expression 1 will have some environment, expression 2 will have certain environment, and this is happening. If at all this type doesn't match, in that case there will be error. So this is how you are assigning certain conditions, rules, or I should say semantic meanings, right? So here you can check the type of the expressions, type of the variables, whether it is matching or not. If at all it is not matching, you will not allow this to reduce, right? You will show certain error that this thing is having certain problem. So in this way you will use it. So now assignment is there, expression 1 is expression 2. You will keep these things. So here what we are learning is in these way we can have certain kind of rules, semantic rules, which can be kept in the with the grammar to make it I should say syntax directed definition. So when it is applied, actually it will be called as translation. This translation can be S attributed, this definition actually can be S attributed or L attributed. Let me tell you about these things. Suppose this syntax directed definition that uses a synthesized attribute only, they are known as S attributed. S attributed definition. And another set of these can be L attributed. Definition. So what will happen in synthesized? It will only use synthesized attributes. Let me write only synthesized attribute. Okay. So every attribute that will be used in this case of S attributed definition, it will be synthesized attributes. However, in L attributed definition, what will happen? It can be synthesized, means the attributes can be synthesized. Why I am using I? Synthesized. As well as inherited. Let me write as inherited. So both the attributes can be used here in L attributed definition. So these were something that you should know about the syntax directed translation. One more thing that you can understand is in S attributed, since it is synthesized, so all these semantic rules or actions, what you say, they are in right in of the production. Okay. However, in L attributed syntax, these semantic actions can be anywhere in the right hand side. Okay, you may not understand like this. Suppose you have certain example. Suppose we take the example of that production. E gives E plus T. We remember this thing, right? So what will happen with this example? Suppose you have E gives E1 plus T, and E gives T, T gives T1 into F, right? And T gives F, and F was what? It was either E or it was digit, right? So F gives digit. So in this case, what you can do is you can assign certain rules here. Along with this, there will be rules. Let me take different color. So along with this, you will have different rules. What will be the rule for this? You will have E dot val is equal to E1 dot val plus T dot val. You can have other rules as well. If you want to define certain variables, you can have to define certain stacks, or you want to create new nodes. These all the things can be done. I am just writing in a short that this can be a rule that you want to apply. Similarly, here you want to apply like E dot val is equal to T dot val. You can apply here what it can be into, right? So T dot val is equal to T1 dot val into F dot val. Here you can apply as T dot val is equal to F dot val. Here you can apply is equal to F dot val is equal to E dot val. Here you can apply as F dot val is equal to, suppose what is the literal meaning of this digit, right? So it can be digit dot whatever. Usually you can write it as lex val, lexical value, whatever it is. So you can assign here. So what will happen if you will have a tree where you have something like this? What will happen? You will have certain digit. The digit values will be multiplied or whatever. You will have another value here, right? Suppose maybe it is T, right? And then this is E. This is another E. So what you are getting here is E dot val is equal to E1. Why we are writing it E1? Because it is also E. However, E dot val and E dot val will be same, so it will add the value of E. However, we want this E, so we are just keeping it name convention different E1. E1 dot val plus T, right? So you will T dot val. So you get this value, add this value, you added it. Now, but what happened? With this it is okay, but you may have one more production here. Suppose this thing L gives E, hello, E dash or E, whatever you want to say. So when it will reduce, what it will do, it will print your value. You can have this, print, what you will print, E dot val. Here it was E drives T, so you were storing the value of T into E, right? In here it is also similar, but you are, in place of storing, you are printing it. Here also you can print it, no issues. While it was performing this, you can print, you have this statement, along with this you have another statement for printing. So in this way you can use this syntax diacrit translation. So you can perform type checking, whatever you want to check here, right, whether the type is matching or not. If the type is not matching, here straightforward you can show that certain error is there. So you can use it for whether this was something expression statement. You will have certain expression for assignment, we will have for other things like declaration. It will perform type checking and show whether it is there or not. So for all these things it will use the symbol table, right? So storing the information related to the IDs and those all the things. Now when you are talking about the stack for these things, reduction, you will have suppose earlier you will having just E, now you will have for value also, whatever for val, so for val also you will keep on keeping the values as well as so that it can be popped, used and replaced. These kind of things can be done. Along with val, if you have certain more variables, you can use more stats with them, no issues. So these are certain things you use. So certain times you may need to resolve, you may need to see whether it is shift operation or reduce operation. So these are certain things that we have to see in this syntax diacrit translation. What happens for the given grammar, you have semantic rules as well. They can be S attributed or L attributed definition. Okay, so I was telling you, like here in S attributed we kept all these semantic rules after it has ended, right? But in L attributed, what I was saying, it can be kept in between also, that okay, this much part has been covered, this has been successfully executed. We can keep some rules here also. We can keep it like here also you want to print something. Okay, it can be done, but it is possible only in L attributed, not in S attributed. So S attributed, you can understand, it is always coming from bottom up, right? So in L attributed, you can see you get the inherited attributes as well, right? So it will be generally in top down. So this is how you understand about this L attributed and how this semantic rules are applied in this case. So with this we will end this video, and we will try to see more things in next video.